OK, so let's take a look at what we have to add to our pipeline. So we have our in order fetch, out of order issue, out of order write back, and in order commit processor that we had before. Note it had variable length pipes, it had a reorder buffer, it had a future store buffer, it had a scoreboard, it had an instruction queue. So it had all the structures we talked about last time. And now we're going to add 2 more structures to it. And we're going to modify the structures that are there slightly. But let's talk about what this is going to do. So the first structure we're going to add is a free list. And the free list is going to keep track of physical registers that we can go use. So the physical registers will probably have more physical registers than we have architectural registers. But you need to keep track of which ones are free to be used, because we're going to basically be allocating and deallocating from the number of physical registers quickly as we execute. The other structure here we call the rename table. Sometimes this is called the RAT, which is the sort of the Intel nomenclature for this. Or actually, the RAT is either this table or the table that we're discussing in the Thomas-Uhl algorithm variant of this, but they're very similar. And what this table does is it's going to map from architectural register to the most up-to-date version in our physical register file. So it's going to say, we have an instruction that's sitting here at our decode stage. Where do we go find the value? Because this gets complicated. We just renamed everything. We have different names for everything. It's in some physical registers. We need to go figure out where that value is. And that's what this table does. We're also going to add 2 fields to the reorder buffer. I'll talk about that in a second. And we're going to want to increase the size of the physical register file so that we can get more performance. If we have the same number of physical registers as we have architectural registers, and we need to have at least 1 physical register for each architectural register, we're not going to get any more performance from having a register renaming step to our pipe. OK, so this is kind of for completeness, where everything gets written in the pipe in time. 2 things I want to point out here. The free list gets updated at the front and also gets updated here at the end. And the condition that you need to deallocate a physical register gets a little complicated. But we'll talk about that. And the rename table gets read up here, because that tells you where to actually go get the value. It also gets updated here when we actually emit an instruction down the pipe. And we also want to update some pending bits when we get to the end of the pipe, so that it knows whether to go sort of pick up from the physical register file or the architectural register file for rollback issues. OK, so let's jump into these data structures and see what we add. OK, as I said, we're going to add stuff to the reorder buffer here. Now, our previous reorder buffer looked very similar to this. We had some state, whether things are pending, free, or finished, where we said dash dash represents free, and F means finished. That means the instruction got to the end of the pipe and is waiting to commit. We had a bit that says whether it was after a branch. You might have multiple of these bits if you allow multiple branches in flight. A bit that says it's a store or not. A bit that says whether it writes a register. So this says whether the destination is valid. And that's important for us to know, because when we get to the end of the pipe, we need to know whether to actually commit some state into the architectural register file. And we have a field here, which we had before, which was the physical register file specifier. So this tells us where to go read from. That's all good. But now we add some extra bits here. The first one is a architectural register file specifier. OK, so this gets a little complicated. What are we thinking about here? Why do we need this? Well, when we get to the end of the pipe, and we're going to do commit, if we go back and look at this picture here, in the commit stage, we take something from the physical register file, put it into, and the reorder buffer drives this. It says, OK, copy that into the architectural register file when the commit occurs. Well, now we've renamed everything. So it's not an identity map from physical register number to architectural register number. So we need to know where to actually go write in the architectural register file. And that's what this does. It just tells us where to go write. So this is where we read from. This is where we write to when this instruction, let's say it's the most recent instruction here, this turns to finished. It's going to go commit. We read the value from here. We write it into the value pointed to by here. And then we have one other field here, which is a little bit odd. We have the previous physical register. Why would we need that? That doesn't make any sense. It was the what is this doing? So this is something we actually read out of the rename table at the front of the pipe. And what it's going to tell us is it's going to tell us, let's say this was register 4. This is where the in-flight physical register is. And this is the previous physical register that held the value of register 4 before we did the update. And the reason we need to know this is when we hit the end of the pipe, we need some way to deallocate physical registers. And we're going to use this to track that. And we'll give an example in a minute. But what this is really going to do is it's going to say, oh, we wrote to the new value of register 4, which means that the in-flight value, let's say it was register 4, physical register 27, and the new one is physical register 30 or something like that. We need to deallocate physical register 27. And we can do that when we reach the end of the pipe by committing this instruction out of the reorder buffer and cleaning up all the state. OK, a quick picture here of the rename table, the renaming table. This is indexed by register. P tells us whether we have a write in flight. So it knows that that value is not in the architectural register file. And preg here just tells us where in the physical register file to go find the value. And this is really important when a subsequent instruction that's looking for that value shows up, and it wants to get that value before it hits the architectural register file. It looks here. This tells us. It tells us, oh, it's pending. It's going to be here in a little bit. Together with this and the scoreboard, we might even be able to bypass it early in a good day. In a bad day, we have to wait for it to get to the physical register file, but it's a lot better than having to go pick it out of the architectural register file. And finally, we have a free list. And this is literally just a bit per physical register, which is very different than a bit per architectural register. And it's just going to have, let's say we have big N physical registers, or I don't know, we have 256 physical registers. And we have a bit saying whether that register has been deallocated and it's ready to be used for future register renaming, or whether there's a instruction using that physical register, or it's waiting to commit to the architectural register file. This will tell us that information in this table here. And just a bit that says whether it's free or not. Pretty simple. Actually, before I go on here, I wanted to make an interesting observation. Where does this register renaming become really important? Well, if we go look at something like the original Intel architecture, they had 8 registers. And if you want to run high-performance code, you have to reuse those registers pretty quickly. So they got register limited very quickly when they tried to build faster and faster processors. So they had to introduce register renaming quite early in the Intel microarchitecture implementations. And they had many, many more physical registers than architectural registers very quickly. Because 8 isn't going to get you very far. They can have like about 100 in-flight instructions. And by definition, you can't have that many in-flight instructions if you maintain write after write stalling effectively, because you're going to have to rewrite some register. It's kind of like a pigeonhole problem. If you have more than 8 instructions, at least one of those instructions is going to cause a write after write dependency, and you're going to stall the pipe. So they're not going to be able to have, let's say, more than 8 in-flight instructions pretty quickly if they did not do register renaming. So they did register renaming very quickly in their pipelines. OK, so this gets us to the eye chart here. Let's walk through a basic case of what's in all these different tables as we execute our basic simple code here. On the top, we have the 4 instructions, 2 malls, and some adds. This was our original test case. Note there is all these dependencies through register 4 we need to worry about. There's both read after write, write after read, and write after write dependencies. We're going to execute it quickly here by pulling, as you can see, this add fires early or issues early, the final add. And this is really driven by the register renaming. So let's take a look at what happens here. And let's try to interpret this. Here we have cycles. Cycles are also across the top of the stage. We show what's in the decode, issue, write back, and commit stage of the pipe. We leave out the execute stages because this is too much to draw here. And it's drawn at the top in a different form. Let's first look at the rename table. So we're at the rename table, or we're actually going to say we only have, for clearness here, let's say we only have 7 architectural registers. But we're going to have, let's say, 11 physical registers. So we're going to have more physical registers than architectural registers in this example. We start off and we say, OK, well, register 1, if you want to go find architectural register 1, the value's in physical register 0. And we can basically just, we just come up with some allocation. And the circles mean that it's not pending. It's not in flight in the pipe. That's just sort of the base case. Everything is, the pipe has been relaxed. Everything is allocated. And we just do a basic allocation here at the beginning. Now, as we go to execute, some interesting stuff starts to happen. First thing that's going to happen is we're actually going to here issue this instruction which writes to register 1. We need to rename this at this point. Register 1, we have to rename to something else. So in this table here, if we look, we rename register 1 to physical register 7. OK, that sounds good. What happens next? Well, we next sit here and we try to execute this instruction here. It's this mall. And it goes and tries to read register 1. When it goes to read register 1, though, we can go look at the rename table and say, oh, well, that's actually in flight, and it's in physical register 7. So if we go look over here, we can draw this and say, oh, that value is actually in physical register 7, and it's currently not ready, maybe. But P4, the other input, register 5, OK, yeah, register 5 got renamed to P4, is ready. So it's ready to go. OK, one other interesting thing that happens here is we can see that as we go to allocate this, we have to remove it from the free list. So this list here is just a list of all the free registers. We start off with 4 free registers, and we sort of narrow it down as we start to do writes. And at some point, we run out. So I wanted to make an important note about this, is that when we run out of physical registers, we're going to have to stall the pipe, because we can't do any more renaming. We can't issue more instructions at that point. So that's really important to realize, is that when you build your machines, you have to have enough physical registers that you don't run out very often. Now, it's possible that you could still run out. So let's say you have hundreds of in-flight instructions, and you only have, let's say, 64 physical registers. You might still run out. But the probability of that happening might be relatively low, and your utilization, and you sort of bake into this your CPI. Your CPI may not be less than 1 or may not be low. So the probability of that actually happening, you may not worry about it too much. Another cute little story here is there's actually been some interesting bugs in processors around the free list. So there were some alpha processors where they actually leaked free list entries in their register file. So what happened was if you ran a certain piece of code for a long enough period of time, all of a sudden this processor just ground to a halt because it was not able to allocate more physical registers, and it ran out. It ended up with fewer physical registers than architectural registers, and the machine just stopped. And this was a sort of well-known bug in some of the early alpha. I think this was actually in the first where was this? I think this was in the 21.264 had this problem. they fixed it, and they pulled those chips off the shelf. And that's a really bad thing to have happen in your processor. Kind of embarrassing. But as I said, if you run out, you're not going to be able to issue more. But in this case, we made sure we had enough. So we're not actually going to see any stalls. And let's look at how things get on the free list here, because that's a little bit interesting. In our reorder buffer, I said we had extra fields. If you recall, we had the previous physical register that this was allocated into. So if we go look at this instruction, which is the first instruction we go to execute, that mul, R1 was in P0. So when that instruction commits, we actually put P0 onto the free list. And we're going to look at a case in a second why you can't do it earlier. Because it seems like you should be able to basically deallocate physical registers earlier. No one's probably going to be reading that value. Why can't you just get rid of it early? But we'll look at in a second a test case that's a problem with. Let's see, any other fun insights here? That's about it, what I wanted to get across from this diagram. As the code continues on, we end up with more and more free physical registers. One thing I did want to, just to walk through this to understand this a little bit, let's say we have this instruction here, which is our, 1, 2, 3, 4. It's our last instruction that we execute. Let's go see what it's doing here. So it writes architectural register 4. So we have to store that in the reorder buffer because we need to know where to go to the write. We had allocated P10 to that. And we did that right here when we actually issued it. So we pulled it off the free list. And the previous thing that it wrote was P8. So when that ultimately commits, P8 is going to end up back in our free list. So that's a nice little thing. The circles just show when the values are no longer pending. So they actually are not in the pipes anymore. And you can see that continuing here. This instruction here, which is the second multiply, when it commits, it's going to free up P3, so P3 ends up on the list, P5 ends up on the list, P8 ends up on the list. And then when we see true read after writes, for example, right here, we need to make sure to pick up that correct value. And we do that by looking up in the rename table. So let's go find that in this chart here. So instruction 2 is, let's see what it's doing here. So that's going to be right here. It's waiting on P8 to become ready in order to issue. So it's sitting in our instruction queue, and it's just going to stall. It's going to stall all the way out to here. Or it's going to stall to right there. And that's when it comes out of the instruction. OK, so let's look at freeing up physical registers and what is a good policy for freeing up physical registers. So we're going to have a different piece of code here we're going to look at. It's going to be just a bunch of adds. And we're going to look at this code has some read after write dependencies in it, namely R1 there. And let's say we try to go execute this. Well, we're going to, here's some execution order. And we're going to look at, or sorry, that one there is what I meant to go point at for the read after write. We have a write after read dependency here. So let's look at some execution order and see what happens. Let's say we allocate physical register 0 at the beginning somewhere for register 1. And then when we do the commit, we free it up in our free list. Well, lo and behold, another instruction in time comes along here and allocates into physical register 0, and it goes and writes to it, and we free it up there. This instruction here, which we had renamed, we had renamed R1 for, and we go to try to read this value, goes to do the read, and it looks in physical register 0, and it gets the wrong value. Ooh. Yeah, we don't want that. So what's a good policy here? Let's say instead we don't free up a physical register until someone else goes to write that physical register, or a subsequent instruction goes to write that physical register. Because then we know that that physical register is in use or could be in use by other readers of that value. So if we look at this case here, let's say we write physical register 0, and then we allocate a different physical register. We allocate physical register 2 for this right here to register 8. And then we deallocate when we go to overwrite register 1. So by doing that, we know when this R1 gets written that no one else can possibly use that physical register that is after this instruction in program order, because we overwrote it. So that value is no longer visible. So that's pretty nice. So that's the a very good heuristic or a very good way to get this correct is you can just keep the physical register live until you rewrite the physical, or you rewrite the architectural register that physical register maps to, and then at that point you can remove it from the number of allocated physical registers and put it on the free list. If you do it early with an out-of-order execution pipeline, bad things can happen. You can go read the wrong values. OK, so this brings us to a couple optimizations on register renaming. Biggest one here is you can try to combine the architectural register file and the physical register file to save space. And the insight here is if you go to try to combine these two things, you can store the architectural register value and the physical register value in the same physical storage location if that physical register is no longer pending. So if there's nothing in flight to it, and you don't have to roll back, and if you're just going to roll back to the same value anyway, why keep extra space for this? One change you need to do here is, so you're going to remove the architectural register file, but you still basically need to know when you go to do a rollback of some speculative, say you take an interrupt or you take a branch mispredict, you still need to know where to go roll back out of. And we're going to do that by, let's say, having a second renaming table here, which allows us to keep track of just the architectural state. So we have a speculative renaming table, then we have an architectural renaming table. It just has pointers in it instead of actually the values at the end of the pipe. And what's also nice here is instead of copying values, we don't actually have to move something out of the physical register file into the architectural register file. Instead, we just have to update a pointer in a table now. And we did the copy. Could potentially also make rollback easier, because we just have to update some pointers now instead of actually copying an entire register file, which can take a while or requires lots of ports or something else. So you can have a little table there to just do this remapping for you. And as I say, you can typically get away with less space than having, for the same performance than if you were to have two separate structures. One of the downsides is you might need to have more, depending on how you implement this, your architectural register file and your physical register file are now together. It may be bigger. So your register file access might be a little bit slower. Something like that could be a downside versus having it in two separate partition structures.